In this video, we're going to be looking at the concept of objects and systems and applying them to molecules, atoms, and charges. This is a very important topic that we're going to be working with because when dealing with the atomic level, we don't see anything that takes place, and it's very easy to be confused on what's actually taking place inside, especially when dealing with electricity. We're not going to deal so much with chemistry, but we are going to be dealing with a lot with electricity and waves, and there's molecular motion involved in these cases and subatomic motion in these cases. And people's confusion often comes from the fact that they're not visualizing what's taking place because we view things inappropriately. So today we're going to be taking a look at how we can apply the concept of object systems to the subatomic or atomic. So here we have a really large rock, and the question before us is this rock an object or a system? And for most people, when looking at this rock, it's really simple. It's an object. You know, it's got a size, it's got a weight. There's nothing else really to take place with this. But as a physicist, we need to recognize that this is not just an object, but it's actually a system of molecules. And even if they aren't doing very much right now or moving around, they could. And I'll be honest, even though I said as a physicist, you got to realize that this is true for anyone, whether you're a physicist or not, that you should be able to look at something that people think is really simple and realize that odds are it's going to have more complexity to it than you're realizing. And even if it's not being shown, it could come out later on. So let's be honest, if I take this rock and I heat it up, the rock can in fact become a liquid. There's no explanation for that if it's an object. I could actually heat up that liquid to the point where it literally evaporates. Some people don't realize that, but you could actually evaporate a rock. You don't want to be near the heat source that can do that, because if it can evaporate rock, it will definitely evaporate you as well. Okay, but there's no explanation for it unless you realize this rock is actually made of various things. So we're going to actually look at water instead of a rock right now because it's an easier thing for us to visualize. And so here we see the states of matter. We can see that we have water as solid ice. We can see water as a liquid. We even have water vapor right over here. And in your earlier classes, we turn around and say, well, that's because of the arrangement of the molecules. You know, here are the molecules for the ice, and they are side by side. They're locked rigidly in place. There's not a lot of movement in there. So this molecule here will stay where it is all times, while here we have a liquid. The molecules are able to move around a bit. So even though there's this molecule over here, he can actually move around over here a little bit. It can't really go that far. And if I have something, let's say, like a vapor, well, then those molecules are just moving quickly and they're spread out. And even if I start over here, I can move all the way over here without an issue. And it's all kinds of random chaos. And this is why solids will always retain their shape and volume regardless of the container that they're in, assuming the container is large enough to hold the object. Fluids will always maintain their volume but will conform to the shape of their container. And a vapor, well, that will not maintain volume. It will always take the shape and volume of the container that it is in. And so we have described this all as a system of molecules. But the reality is this model isn't exactly correct because water molecules are more than dots. They have subparts to them. Why does water react with some chemicals but not with others? There's no explanation for that if it's just a round dot, just an object. But the truth of the matter is a water molecule is actually a system of two atoms. I'll be honest, if I'm dealing with elementary school kids and I just want them to get the difference between a solid and a liquid, I don't need to talk about subparts of a molecule. We can just describe it as a thing. But when I want to talk about now how water molecules act differently than other molecules, I need to now talk about their parts. I need to realize that there's actually a group of atoms there. And so I have two hydrogens and an oxygen. But now I'm not looking at the atoms as a system. This is just something, a system of three atoms. What makes up the atoms? Who knows? No one cares. Then all of a sudden we start talking about water molecules and kids start asking me really annoying questions such as, why does it look like an upside down Mickey Mouse? Teacher, you just said that the water molecule is slightly polarized. Why is that? Teacher, I saw somewhere along the way there was H, HO, H2O, but I can't find H3O. Why is there no H3O? And what's wrong with H4O? And the teacher goes, oh, can you please stop asking these questions? And that is often because that particular teacher isn't looking at the atom as as a system, but actually as an object. And these questions are all really good questions and very easily answered once we realize that the atoms themselves aren't objects, but they are also systems. They are systems of a nucleus and an electron cloud. And the shape of the atom has part to do with the shape of the electron cloud. Also, the polarity has something to do a bit with the shape of the electron cloud. And so we have these parts. But why is the oxygen cloud larger than the hydrogen cloud? Well, once we take a look at the cloud and realize it's a system of electrons, we can see that the oxygen has more electrons in it than oxygens. We can also then realize that the reason there's no H3O is because there's no more room for hydrogens to join up with the atoms because there's only so much space, there's only so many electrons that can fill in the orbitals, and once we get to H2O, there's no more vacancy allowed. So there we are. But why does an oxygen atom have more electrons than a hydrogen atom? That doesn't make any sense unless you realize the nucleus, of course, is a system as well. Not only that, but somewhere along the way you learn about isotopes. Now, isotopes are atoms that have the same number of protons, but they all have different atomic masses. Why do they have different atomic masses? And why do they have a nuclear charge? And that comes from the fact that they are a system of protons and neutrons. And sometimes some atoms, although they have the same number of protons, will have different number of neutrons. And so they have the same electrical property, but a different mass. And so again, we are realizing that something that is a really simple object, such as a rock, is actually composed of many subsystems. And so nothing is really as simple as you'd like to think it is. In fact, when we get to this point here, we finally often kind of consider things to be set. These are the smallest things that we're often looking at, and we start to use things as a basis for everything else, such as the charge of an electron or proton. That is often called the fundamental charge. This is the smallest charge that we've ever seen by itself. We're not saying it's the smallest charge possible, it's just the smallest charge we've been able to observe. And so that's the charge of a single proton or electron. We use the letter E to signify the fundamental charge because we found electrons first, because they're on the outside of an atom. And I'll be honest, it's very weird when you tell people that in the very beginning. It's like, well, electrons are really small, protons are really big, and we found the electron first. How on earth did that happen? Well, when you view the atom as actually a system, you can see, well, the electrons are on the outside. That's the storefront. That's the hostess or host at the restaurant. Who do you see first? You see them. So that actually makes a lot of sense that even though that they are the smallest part of the atom, they are on the outside. So of course we would see them first. We don't have a letter P for the charge of a proton because the number is exactly the same. Why use two variables for the same number? So the fundamental charge is the charge of a proton, which is the letter E, which is the same as the charge of an electron. E is not a negative number. It's just a number. It's not positive or negative. If I have the charge of a proton, I should have a plus sign with that to show that it's a positive charge. If I have an electron, I should have a negative sign with the E to show that it is a negative charge. The number itself, E, is 1.6 times 10 to the negative 19 coulombs. This is something that we're going to talk about later on throughout the course, and this is not a number you ever need to have memorized. There is no fundamental reason that you need to have this number memorized. If somewhere along the way it does become so important in your life that you will need it to be memorized, you will probably memorize it because it will be that important to you. And if not, it's something you can always look up. When we take a look at the nucleus, we see that sometimes the nucleus can do very weird things. We have things that are called nuclear reactions. The nucleus itself can change. One of the weirdest things that we see is radiation, specifically something called beta radiation. Beta radiation is when a nucleus will either absorb an electron or, even more weird, shoot an electron out. Now, think about this for a moment. If a nucleus is nothing but protons and neutrons, and all of a sudden this nucleus shoots out an electron, and the nucleus becomes a little bit more positive all of a sudden, where did that electron come from? That doesn't make any sense if neutrons and protons are objects. And the answer for this was really simple. Clearly, a proton is not an object. It's a system of something. Neutrons are not an object. They are a system of something. There's some smaller components that make them up, components that we can't see directly, but we can see their effects. We have never seen anything like this with an electron. So we believe, and please notice, I say believe, not know. We believe an electron to be a fundamental particle. It can be considered an object because there's nothing else there that we know of. There's no evidence of that. I could be proven wrong on this tomorrow, and I totally accept that. This is just based on the stuff that we know. But for protons and neutrons, we have seen this weird change where protons can transform into neutrons if they get hit by an electron, and where neutrons can split into a proton and an electron. This means there's something else inside there. And we call those things quarks. Quarks have a charge that is smaller than E. Now, if you notice, I had said E was the smallest charge we've ever seen for anything on its own. So how can quarks have a charge smaller than E? Really simply, we've never seen a quark. We don't know if they truly exist. All we know is that protons and neutrons will sometimes transform, and this is a model that explains it. But we have no proof that this model is correct. And based on our theories, if our theories are correct, we'll never be able to find a quark. According to the theories that we have on quarks, if I was to somehow be able to reach into a proton, now keep in mind, for me to reach into a proton, I need a device smaller than the proton. So for me to reach a proton, I need to build something out of atoms that's smaller than a single proton that makes up atoms. That's never going to happen. But if I was to somehow magically tap into my inner Harry Potter and pull out a quark, there would be so much energy that would be needed that the theory is that this would actually create more matter, where I would actually create 3 quarks. One quark to replace the one that I just ripped out, and 2 other quarks to keep the guy I just pulled out company. So if our theory about quarks is correct, we're never going to be able to find a quark on its own. So we can still consider the fundamental charge E because as far as we'll ever see the universe, that's the smallest increment that we will ever get to experience. So E again is our fundamental charge. We're not going to deal with the chemistry aspects of this, but we are going to be dealing with electricity quite often, and this is something that a lot of people just dismiss, and they really have no understanding of electricity. And one of the reasons we dismiss it is because it's so common. We live in a digital age. Everything is electronic now these days. And so we see electricity constantly. It's no big mystery in terms of, yeah, it runs off electricity, but I don't know other than that, but I don't care. And we run into serious issues when you actually have to manipulate it. And in this course, you have to understand electricity. And I'll be very honest. If you're ever going to live in a world that's dictated by electricity, you should really understand it. It's amazing how much you will be taken advantage of in terms of business and home repair and items that you can buy just because you do not understand the very basic ideas. And most of the stuff that we need is going to be really based on this really simple ideas that you could do yourself if you understand the basics of electricity. Now, here we have a very simple circuit where we have our battery. Batteries have a positive side and a negative side. The side that has a little bulge always has a plus sign. The part that's flat has a little negative sign. I have a switch right over here that I have in a closed position so electricity can flow through this. I have a little light bulb that could light up. And I have this section of wire that connects everything together. And we're going to focus on the electricity that's flowing through the wire. Now, something that's really weird that most people don't catch, and it's always funny when they say, yeah, I understand electricity. Yeah, it's not complicated. You hook up a battery and things run. Okay. Well, electricity is the flow of what kind of charge? You ask that, and most people will tell you, oh, it's the electrons. I learned that in chemistry class, or I learned that in elementary school or junior high. The electrons are on the outside. It's a metal. You've got what's called the sea of electrons. Electrons aren't bound to anybody. So when I hook up a battery, they just flow. Okay, that makes sense. But riddle me this. If electrons are negative, and this is the positive side of the battery, why on earth is the electricity flowing out of the positive side of the battery and returning to the negative side of the battery if it's the flow of negative charges? Because if they were the flow of negative charges, I would expect them to leave the negative side of the battery. And they would flow to the positive side of the battery because negatives want to go to the positives. This doesn't seem to make any sense. And the reason for that is there are multiple ways we can view electricity, and we have to view our atoms as a system. The truth of the matter is there are two kinds of electrical current flows that we can consider. We have what's called electron flow, and we have what is called hole flow. Both flows are correct. It just comes down to which one is more convenient for you to work with. And for most electronics, especially when dealing with semiconductors, and that's part of all of our transistors, is hole flow. Hole as in a hole in the ground, not a hole like a whole piece of bread. So we're going to clean up the wire just a little bit and to make it a little bit simpler. Here I have a section of wire. There is my nucleus, which is positively charged. I have my electron over here that is negatively charged. And the total charge in my wire is actually 0 at this particular time. So as of right now, it's as if I have my switch turned off. So you can see my switch is in the off position. Electricity cannot flow through this, so I have absolutely no electricity at this time. And so I have this wire where I have both positive and negative charges equally balanced, and everything is neutral, and I have no electricity that's flowing through. And that makes perfect sense. Now all of a sudden, I'm going to go ahead and I'm going to turn this on, and now electricity flows. Well, what's happening now? Well, if negative charges are the charges that move, and they want to go to a positive charge, then these electrons want to start moving over to this battery. But they're not all going to move at the same time. The guy closest to the battery is going to notice that there's a chance to move over, so it's going to move over first. So this guy is going to leave the atom, and actually instead of going forward, down, is actually going to move back towards the positive side of the battery. Not a whole lot, just an atom's distance. But when that happens, I have now a hole in my atom, like I would have a hole in the ground or a hole in a piece of bread once you punch through it, or a hole in a piece of paper, because you shouldn't be punching holes in bread. That just sounds weird. But the bottom line is there's a hole in my atom, and when I'm looking at this, I see a positive charge. See, I don't see it anywhere else because every proton is balanced off an electron. But this one atom now is off balance, and I physically see a positive charge. Now, what happens? This electron down below sees that positive hole, and it goes, hey, wait a minute, that looks kind of nice. So it's going to move over. And when it moves over, the hole now moves in the opposite direction. I'm outside the wire. I don't see the electrons. I don't see balance. Okay? It's kind of like the news. They don't show you things that are balanced. That would be really boring. Well, ladies and gentlemen, today there was really nothing that really happened other than people got up in the morning. They told their family that they love them. They went to work. They came home. They ate some food, and they're going to bed, and it was just a wonderful day. We don't want to see that. That's not interesting. We want to see turmoil. We want to see things that are off balance. That's when we notice that things are happening. And so that's what we have here. I see that this positive charge is moving towards the negative. And as this electron will now be attracted to this positive and it moves over, I see again this positive charge moving towards the negative. So this is hole flow. Hole, again, like a hole in the atom. It is not more or less correct than electron flow because, let's be very honest, electrons are moving towards the positive charge. But we don't see that from our point of view. And so we will often use electricity from a positive hole flow point of view. And the only way we can actually explain why this happens is to recognize that electricity is actually a complex system of protons and electrons, where electrons are going to be moving in one direction, making holes that would travel in the opposite direction. All right. This can be a little bit of a confusing topic for people. If you're getting this, that is awesome. If not, that's totally okay. The purpose of this video is not to get me out of teaching this stuff, but simply to get you some exposure to it before we discuss it in class.